Okay, let's start off with the first challenge problem. We know the density of molecules in outer space. The unit for density here is molecules per liter. So I'm just going to record what I know, hopefully make sense of it after. Assuming the temperature is 120 degrees Celsius, so I'm going to go ahead and record temperature but in kelvins. And we are trying to figure out what would be the pressure in pascals. All right. So looking here, it doesn't seem like we know too much. Remember, we do know our constants. Since I don't have double of anything, I'm probably not going to be using Boyle's, Charles, any of those laws. So what I'm going to be looking for, most likely, is the ideal gas law. I have one temperature, I'm looking for one pressure. Here I see a unit that deals with volume, and then maybe I can turn molecules to moles, and then I would have V in R and T. I could solve for pressure. So that's my game plan. I want to use PV equals nRT. So I have temperature, I have R. I'm going to use this to find volume, and I'm going to use this to find moles. So then I could solve for pressure. All right, I'm going to take this density right here and try and get it to moles and liters. To make it easier to visualize, since we're solving for pressure, doesn't this become nRT over volume? And isn't this molecules over liters? But what we really want is moles over liters. So I can just use this one number to get both moles and volume knocked out. All right, so if I have Avogadro's number of molecules, I know that equals 1 mole. Molecules are gone. I'm going to be left with moles over liters, and so I can just plug that in the formula. So sorry if you'll hear my dogs in the background. All right, so now I have moles per liter, I have temperature, I have R. I'm going to solve for pressure. Pressure equals N over V. I'm going to plug this in. It's per 1 liter, so it's like that on the bottom. R and T. So pressure equals you'll see that's not an answer choice, and it's because we found our pressure in ATM, and the question specifically went at pascals. And they gave us the conversion for it, so multiply by 1 ATM under 101.325 Pascal. Right, and so we should get 1.3 times 10 to the negative 11 Pascal, which is A. All right, so now I'm going to go on to the next challenge problem. So take a second to read number 10. We know pressure, we know volume, we know temperature. This one's not too bad. I guess it's not asking for moles, it's asking for hydrogen atoms, but if you have one of each of these things, we could use ideal, find moles, and then moles to atoms. But pay attention, it's hydrogen atoms, it's not total atoms, so we have to keep that in mind. And also make sure your units are what you want them to be for the ideal. So yes, yes, no. So let's go ahead and turn this into kelvins. Alright, so I'm going to use PV equals nRT. I'm going to go ahead and plug in what I know and solve for moles. N, R is 0.0821. Alright, use your calculator. And I got 0.11567, and that's moles of gas, and the gas is C2H2. So now, can you go from moles of gas to hydrogen atoms? Hopefully so. So let's start off with this. Nope, 0 is before the decimal. Let's say 1 mole of C2H2, and since I'm trying to go to atoms, I need to get to smaller units, so if I have this compound, I'm going to go ahead and get to molecules first. If you want to say 1 mole of this equals 2 moles of H and then get to atoms, that's fine. Our steps will just be reversed, no big deal. So equals Avogadro's number of molecules of C2H2, and then 1 molecule of C2H2 equals 2 hydrogen atoms. So there's 2 hydrogens per every one of these. If these two are reversed, no big deal. Alright, so let's go ahead and plug that in. And when you do that, I get 1.39 times 10 to the 23rd hydrogen atoms. And if you forget this last step to multiply by 2, he did provide that as an answer choice, so be wary. Make sure you know what you're looking for. Make sure you answer the question. So D is the right answer. All right, let's attempt the last challenge problem. It's a fun one. All right, go ahead and read it for a second, and we'll tackle it. So we have a container, it takes up 12 liters of space, a temperature of 27 degrees Celsius, which is 300 kelvins. We fill it up with 4 grams of hydrogen gas and 20 grams of carbon monoxide. Those two things react, producing a new gas. So at this point, you're envisioning 2 gases, add it together, make a new gas. You have 2 amounts of the gases, right? 1 for each reactant. So what type of problem is this? And hopefully you're thinking limiting, right? That's going to play a part of it. Calculate the final pressure inside the container. So let's think about what the question's asking. It wants to know pressure. Pressure has to come from gases. Carbon monoxide's a gas, hydrogen's a gas, and the product's a gas. But it wants to know pressure after the reaction. So think about it. What's going to be left over after the reaction? Well, definitely product, right? That's the whole point. We're making a new gas. So pressure's going to come from that product. And then you also have 2 reactants. So do you need to know about them at the very end? And hopefully you're thinking yes. Well, since this is a limiting problem, one of those is going to be depleted. the other one will have excess. So the pressure at the very end is going to come from your product and leftover excess gases. And those gases that are in the container are going to exert a pressure on the container because of collisions. So we need to figure out which one's limiting. We can scoot that to the side. How much excess is left over and how much product do I make? And those two gases together can tell us the pressure. Now, what do we need to know about those gases at the very end to solve for pressure? Well, we don't need to know volume and we don't need to know temperature. But what we need to know is moles, because moles of a gas determines pressure. The more moles you have, the more pressure. So let's start with the balanced equation. I try to talk it through, but I'll show you again as we go throughout the steps. So hydrogen gas plus carbon monoxide yields CH3OH. And then let's balance it. 1 carbon, 2 hydrogens, 4 hydrogens. So I'll put a 2 here. 1 oxygen, 1 oxygen. So we're balanced. I'm going to go ahead and do a chart. If you're not a chart person, take your grams of both reactants, work it to the product, figure out which one limits you. So 4 grams of this and 20 grams of this. All right, so this will have a mass of 2, 12 plus 16, coefficient. So I'm going to work these both down and figure out which one of these is my limiting reagent. Alright, so it looks like my limiting reagent is my carbon monoxide. How much of this will I have at the very end after the reaction takes place? Hopefully you're thinking 0 grams left at the end of carbon monoxide. Let's use our limiting equivalent and solve for how many moles of product, because really moles exert the pressure. We don't need to go all the way up to mass. All right, so I'm going to move this over. And this, I'm going to box it in because it's important, is moles of product at the end. And since it's a gas, it will exert pressure. Now, are there any other gases in the container at the very end? Yes, some of the excess. So let's go find out how many moles of excess are left over at the end so we know how much pressure this is exerting. So I'm going to move this over. I'll split it. 0.7143 times 2. 1.429. And I'm going to subtract these two to figure out leftover excess at the end. So 2 minus 1.429 equals 0.571 moles of H2 at the end. So I'm going to box this in. So the two answers that I have boxed in are the ones that are going to collide and create pressure. So now that I know moles of all my gases at the very end, what could I do? So I'm going to add them together, and that'll be total moles. And then what formula do you think I could use if I know total moles, temperature, volume, and I'm looking for pressure? Hopefully you're thinking ideal. So total moles of gases PV equals nRT. I would like to know pressure. 12 liters is my volume. N is total moles. R is 0.0821. And temperature is in kelvins. Let's go ahead and find pressure. Okay, so that leaves us with E. I know they're not identical, but they're super close. Again, it probably depends on like how many decimal places the molar mass was to, how many decimal places we kept in our chart. All right, so that's the end of the challenge problems. Again, most likely would not be on an exam. They take a little long to solve, but you are responsible for knowing how to work them. They are doable, and you might see them on some homeworks.